Now, this is called the match filter. What is the match filter really doing? Just look at it. What it is doing? What it is doing is in this x of t, which is the n number of summation of the function containing terms corresponding to each of the phi I, this fellow is preferentially pulling out the term corresponding to phi I t. So, it is matching itself to a particular component of the signal that is signal contains. That is why the word match filter. The word matching is matching with respect to the desired component, which is the phi I t. And here this correlation type, that is the definition of a correlation between two functions, both are equivalent. It is a question of which way you want to break your head. You want to do it by this way, you want to do it by this way. So, sometimes hardware is more easy to do by this way, and sometimes it's easy to do it this way. So, you choose either this method or this method. Both are equivalent, both will give you same result, but which one you actually adopt depends on your convenience in terms of realizability in terms of hardware. They are simple ideas, but give you so powerful results. We will come hopefully someday into this. If this x of t contains a desired signal s of t and an undesired signal noise, then if you do the same operation here, then you will get two components, one component due to this and one component due to this. And if the component due to this is much smaller than the component you get from the signal, then you get a higher output signal to noise ratio. So, you are able to extract a signal out of noise, and this match filter actually has been invented theoretically for this purpose. When the signals are embedded in noise, then what do we do to get higher output signal to noise ratio? Because remember, input signal to noise ratio, this may be band limited signal. So, the number of phi A's is in this limited, but this is no band limitation here, so there will be a large number of them. So, the noise power is much larger than the signal power at the input terminals, but at the output terminal the signal to noise power is much higher. So, you are able to extract a signal embedded in noise. So, this is how actually match filter originally was invented by D.O. North in 1945 or something, which formed a basis for many developments in communication theory. So, with this way of looking at it, many things which are done in 101 or any other place can be viewed into this format. So, as I said, if phi i's happen to be sinusoids, they are orthonormal. We can normalize it and they are orthogonal. Two sinusoids to different frequencies will be orthogonal to each other, and cosine and sine are orthogonal to each other. Cosine and cosine are orthogonal, the frequencies are not the same, and sine and sine are orthogonal, the frequencies are not the same, and so on, and you know all this. So, that's exactly the properties of my phi I t. So, as long as this phi I t's represent it from minus infinity to plus infinity, any function which is expressed in terms of minus infinity to plus infinity, expanded into the Fourier series. This came out to be nothing but the Fourier series. So, IIT happened to be sinusoids, then the expansion is the classical Fourier series expansion, right. So, one way of looking at it. You also studied sampling. What did you do in sampling to represent a signal in terms of set of numbers? We sampled at different points of time, equally spaced, and so we called it T as the spacing between two samples. So, what I did was I multiplied the signal f of t as a x of t by a series of impulses. What I did in sampler? Spaced, equispaced. When I multiplied this, I got the value of this x of t at this instant, at this instant, at this instant as numbers. And these numbers are nothing but similar to our exercise. And so this should also be forming an orthonormal set. So now I look at this series of impulses in this following manner. Like this. Are they orthonormal or not? Because this and this, when you multiply, is equal to 0. Because this occurring at this instant, this occurring at this instant, that this occurring, this is 0, this is 0 here. So they are orthogonal. Then these are orthonormal. Because any function you take and integrate it, the impulse integrated area under that is equal to 1. So this is an orthonormal set. So the sampling which you have used to represent a continuous signal in terms of a set of numbers, which happen to be the amplitude values of the function at the sampling intervals, can be viewed as a expansion orthonormal set, right. So all the any way by which you convert a continuous time signal into a set of numbers is a orthonormal expansion. It falls under the same category. You can view it in this spirit. Okay. Then what else do we do?